Hello. I recently had a project where I needed to work with one of the ubiquitous LCD display modules, which are just everywhere these days for just a few dollars each. I'd used these years ago, I think when they were fairly new, and I'd really kind of forgotten a lot about how they worked. So for this new project I had to kind of bone up again, at least to the degree that I could complete the project. And I was hitting a lot of websites and so on, trying to find information. A lot of these are put out by Chinese outfits and the documentation isn't very good. Even on the companies that are ostensibly, based in the US, the documentation can be very confusing or incomplete. And I found a lot of websites and YouTube videos that, themed themselves as being tutorials on how to use these, and in fact they would kind of get you to work with them, but they were all based on using a Raspberry Pi or an Arduino this or that to operate them, instead of really how they work in and of themselves. And I didn't actually find anything that covered that, so I thought, well, even though I'm not an expert on these, I do have the ability to get them to work in a basic way. So I thought I would just sort of recap the things I've rediscovered or relearned about them in case it is of use to somebody else who's starting to work with these. So this is an LCD here. It's a single line LCD. You can also get ones that look very similar and they're a little taller and they'll have two lines. Those are the most common, and they're usually 16 characters across. So this is a 1x16 display. 2x16 is also common, perhaps even more common these days. These typically are just a circuit board with a single controller IC. I'm just going to call it the controller from now on, that does almost everything. It does the interfacing, it does the driving of the LCD, and there may be a few odd bits and components related to power supply or the backlight or this and that, but basically it's everything under one chip, and they don't even bother to use a surface mount or something. It's the super low cost mode of just actually putting the IC itself on the circuit board and then covering it with a glob of black epoxy to encapsulate it. And then you'll have the LCD itself on the front, and that's about it. In the old days, these didn't have backlight, but now pretty much everyone you buy has a built-in backlight. And in the old days, when they did have backlights, they were usually electroluminescent, so they required a separate AC power supply for the backlight. These days, LED backlight of one kind or another is more common, and most of the time they're designed to be powered off the same power supply that runs the logic on this, and 5 volts is the most common as far as I've been able to tell. Certainly all the ones I looked at were designed to work on 5 volts, and 5 volts would work for the backlighting, it would work for the module itself, and there's a good chance that the device you're connecting it to also can run at 5 volts. The industry has pretty much standard on a single controller design for these, so it's going to be fairly rare that you find them run by a different controller, at least on these small displays. The most common display controller seems to be the Hitachi HD44780. You're going to see that a lot, and there are other companies that make similar controllers that are compatible with the 44780, even though they may have different numbers. This particular display here by New Haven Display is a new one I bought to have a couple more in my junk box, and it uses a competing controller, but from the outside world it seems to be the same as a 44780, and internally it may work a bit differently, and there may be some small subtleties, but in normal use you wouldn't recognize the difference or tell the difference. So that's an important thing to know, is be looking for the HD 44780 controller on these. Now, another thing that's pretty much ubiquitous with these is you're going to see at the upper left-hand corner a 16-pin connector. Usually it's just a bunch of holes on the circuit board and there's no actual connector on it, because depending what you're connecting it to, you might want to solder a cable in or put a plug header or a pin header or any number of things. In this case, I've put a plug header on it, but again, that's just my choice. And if you rotate these like this, pin number 1 is on the top and pin number 16 is on the bottom. So they all have uniformly gravitated towards and standardized on this 16-pin connector. And again, this is very common and the pinouts are the same. So I've started out here with a piece of paper and I've just put pins 1 through 16, and now I'm going to talk about what those do. So let's start with pin 1. Pin 1 on these is ground. And pin 2 is VCC. And that's usually 5 volts DC. So this is your power supply, and the ground is going to go here, and the plus 5 volts is going to go here on pin 2. Then the next thing you're going to have is the contrast adjustment for the LCD. And this is a voltage between 0 and 5 volts most of the time. So I'm going to write contrast, or CONT there, for contrast. And unfortunately you can't read what I wrote because it's sloppy. See if I can fix that. There, that's a little better. And what this usually is, it can be driven from software through some sort of a digital to analog converter, but really most of the time it's just going to be done with a potentiometer. So it's because it's got to go between 0 and 5 volts to adjust the contrast. The most common thing to do is just take the circuit ground and connect it to one side of a potentiometer, and then the other side of the potentiometer goes to plus 5 volts, or VCC, and then the wiper of the potentiometer comes back and goes to the contrast pin. So this way, by adjusting the potentiometer, you can swing this contrast voltage between 0 volts at ground and 5 volts at VCC. That's a simple way of doing it, and you can do the math to figure out what size of potentiometer that probably is going to be. I would say 10K is probably a good value, but it could certainly be other values as well. You don't want it to be too low or you're going to have too much current going through it. Now the control pins for the controller on the LCD display. There are typically only 3 signals involved with interfacing besides the data itself, and pin 4 is the one we're going to call RS, and that's the common abbreviation for it. And this is considered to be the register select, and these typically have 4 registers in them, 2 of them for reading data from the display controller and 2 of them for writing data to the display controller. But within each type, reading or writing, there's only 2 registers. One of them is called the command status register, and the other one's called the data register. So you have to be able to select between the command status and the data, and that's what this one pin is for. If you leave this set to logic 0, that means it's command. And if you set it to logic 1, or 5 volts, then it's expecting to deal with data. Similarly, pin 5 is the read-write pin, and if you leave this to 0, it's going to assume that you're writing a command or data to the display. If you set it to 1, it's assuming you're going to read a command status or data from the display. So with the 2 bits here, and if you look at them in a binary pattern, there's 4 choices. There's the choice where you're writing command or writing data, or reading command status or reading data. So those are your only choices. Now pin 6 is the clock or the enable. So I'm going to write here clock / enable. And what this is doing is it's looking for a signal that goes from high to low, and on the falling edge of the signal it's going to clock data in or out of the display. So that works along with these. So for example, if you've decided you want to write some data to the display, you're going to set these 2 bits to 0, and then you're going to bring the clock enable signal from a high to a low, and it's going to expect to write data at that point. The same way if you wanted to write data instead of a command, and I've been throwing the word data around loosely. Technically the command is also data, but I'm going to try to stick with the terminology here, and I may have messed up already, but bear with me. So if you want to write actual data to the display, you're going to set RW to 0 and RS to 1, and you're going to bring the clock enable signal from a high to a low, and then you can return it to high or leave it low, doesn't matter. The only thing it's looking for is the falling edge. That's the critical thing, and that's when the data is actually written, is on that falling edge. And of course you can set it up to read command or read data, and do the same thing. You still have to have this signal falling to make it happen. Now pins 7 through 14 are your data / command bits. So this is 0, 1, 2, 3, 4, 5, 6, and 7. And you'll see this is 8 bits long, numbered 0 to 7, and that makes up 1 byte. So that's pretty easy to deal with because most systems can work with bytes. There's an additional mode on these. Most of them have it, and it's definitely supported by the controller that I mentioned earlier, because on some smaller systems you may only have a few bits available. You may only have, for example, one 8-bit port to do everything, and you might need to use up a couple of, or 2 or 3 pins of that port to get these 3 signals, and then you only have 5 bits left to interface with the rest of it. And so Hitachi allowed for in their controller design what they call 4-bit mode. This of course here is 8-bit mode, but in the 4-bit mode it's only using these 4 bits here. So 4, 5, 6, and 7. And all of the data or commands is sent in 4-bit chunks using only these 4 pins, and these 4 pins are disregarded. They don't even need to be connected, but usually they'll be connected to ground. I'm not going to get into 4-bit mode. I'm going to stick with 8-bit mode here. Here's another subtlety. The Hitachi controller is supposed to default on power up to 8-bit mode, but some sources say it actually defaults to 4-bit mode, and I found data sheets for some of the competing supposedly compatible controllers that one of the small differences is that they definitely default to 4-bit mode. So that's something to watch out for when you get one of these. But here's a good thing. Let's say you're just going to work with 8-bit mode and you don't know for sure whether your display is one way or the other. You know, did it default to 4-bit mode? Did it default to 8-bit mode? There's actually an initialization sequence, which I'll talk about later, and that should always be done right after power up on any computerized device that uses these displays. You should always send the initialization sequence, and that works regardless of which mode the controller is currently in or what it defaulted to. It only uses the upper 8 bits, bit 4 through bit 7, and therefore even if the display is defaulted to 4-bit mode, it's still getting the same information during the initialization. But then later on in the sequence it tells it, hey, switch to 8-bit mode. If it's already in 8-bit mode, it still responds the same way. So I'll discuss that in a little more detail later on, but right now just know that you can interface these with either 4 bits or 8 bits of data, and the controller is designed to work either way. So finally you have pins 15 and 16, and this is for the backlight. You have to think about this as just being an LED inside the display module, an LED or LEDs that provide the backlighting. Now on this particular display, you can see here there's actually this white strip behind the LCD, and this LCD is a transmissive type of LCD. What that means is it's like a transparent window that has the transparent LCD in the middle of it, and because it's transmissive, light from the back just goes straight through, and when you turn the LEDs or LCD segments on, then they become opaque to the light and you'll see them as dark segments or characters. There's another kind of LCD known as transflective, and there's other names for that, but transflective is the one I've seen, and that is that it's still basically clear, but they put a mirror of some sort behind it, so all the light that makes it work has to come from the front. It goes through, bounces off the mirror, and then comes back out, and it works the same way, but in that case it's only working off of ambient room light, and if you don't have good ambient room light you will have a hard time reading the display. Whereas the transmissive type has no mirror in the back, and the only way you're going to be able to read the display is if light comes from the back and passes through the LCD and then comes out the front. So in that case, either the back of the display has to be open to a source of light, or there has to be a source of light built into the display, which is the case here. And you can see here there's this white strip, and that's basically a long element that produces light. I believe the data sheet for this says it's LED based, and it does say A and K on there. You can just make it out in gold. That would be for anode and cathode, which would support the idea that it's some sort of LED module stuck back in there, and it no doubt passes all the way behind the display, and you can almost see the very edge of it below the white part of the display, right on the edge of the circuit board, or right on the circuit board underneath the white part of the display. And on the circuit board itself, the foils from that just go out, and there's a couple of jumpers, and looks like there's maybe a diode in there. Anyway, it makes itself back, it makes its way back to these two pins. So what it's really expecting here is the plus side and the minus side of the backlight power. And typically this can be any number of things, but it'll work on 5 volts just like any LED, but you have to current limit it. So you don't just connect 5 volts there or you'll burn something out. What you really need to do is put a resistor in series with either pin 15 or pin 16, most likely on pin 16. And you have to look at the data sheet and see what kind of current they expect through the LEDs, the LED backlighting, and select the resistor appropriately using Ohm's law, and you apply your power supply voltage, you'll apply the LED voltage, you'll subtract the LED voltage from the power supply voltage, and you'll end up with the amount of voltage that needs to be dropped across the resistor. You'll divide that by the expected current through the LED, and you'll end up with a resistance, and that's your resistor value you have to put elsewhere. It's not on the display itself. So that's an important step. So anyway, that's the physical interface, and these lines here will be coming to or from your microcontroller or computer or user port or whatever thing you're connecting it to. Okay, now for the initialization sequence. The initialization sequence involves sending the same command 3 times in a row. And there's a reason for that I won't get into here. It's a little tricky, but it all has to do with being a command that cannot be misunderstood even if the controller doesn't know what mode it's in, or if you don't know what mode the controller is in. After power up, or it's some indeterminate state or state you're just not sure about. And that involves sending on the upper 4 bits only a binary 0011, and then because it might be in 4-bit mode, you don't want to send anything on the lower 4 bits. So they could be anything, but in good practice you're probably just going to set those to ground or logic low. And that's binary, and in hexadecimal it's going to be 3 something, and if you really have set these all to 0, then it'll be hexadecimal 30. So you send that 3 times in a row, and that will assure that the display controller is now initialized, and it's definitely going to be in 8-bit mode. However, you don't want to be sending this after you've been using the display for a while, because then the display will think you're no longer initializing it and that you're doing something else. So this is something you want to send right after you've powered it up, before you try to send it anything else. I've had trouble with these sending this sequence after I've already used the display for something else. If I send it this again, I've gotten some weird results under certain circumstances. So that's just something to keep in mind. So after you've initialized the display, you have to tell the display how you want it to work, given your particular application. And the command for that seems to be the same command as for initialization. The upper nibble, or the upper 4 bits, are also 0011. The difference here is that you might have some bits here turned on. And I think this is where the display can get confused. If it's, for example, in 4-bit mode or something, when you send this, it's not going to get the lower 4 bits, and it's going to misinterpret what you're trying to send it. So let's say we're already in 8-bit mode, and you've already done this, and now you're going to send it this. The upper 4 bits define what type of function it is, and the lower 4 bits contain the details. And I put in placeholders here, N and F. And what N stands for is number of logical lines. So the N here refers to the number of logical lines, not the number of physical lines. This is a 1-line physical display. That's all it has on the LCD, but it still operates internally like a 2-line display. I think this function is probably more useful when you have a physical 2-line display that you might want to have operate as a 1-line display. I've not become really sure that I completely understand that, but I found that this display does not work correctly unless I configure it as a 2-line display. So all the references I found suggested treating this like a 2-line logical display, regardless of the number of physical lines. Whether it has 1 or 2 physical lines, still treat it like a 2-line. So if N equals 1, that means that it's a 2-line logical. So I'm going to replace this N here with a 1. And now F refers to the font. Many of these displays actually only support one font, but there's an option, at least in the codes, the command codes, for telling it to use an alternate font. If you set this as F equals 0, then it assumes the default 5 by 8 pixel font. So it's looking at a pattern of pixels, 5 wide and 8 tall, full of pixels here, and the fonts are all going to be based on that size. If you were to change F to 1, then you would get some other font that uses a different pixel pattern, presumably. But apparently most of these don't actually support that, even though there's theoretically a code. So most of the time you're going to assume that this F bit should be a 0. So this works out to be 3 in the upper nibble and 8 in the lower nibble. So in reality, this code is almost always going to be 3/8 for most normal applications. So that would be one of the things you send it after you initialize it. But you could also send this at any time later on. I don't think there's any reason why you can't reconfigure the display on the fly in the middle of an application if it suits you to do so. I don't think there's any penalty towards doing this as many times as you want or need to. Another common display is your basic, I would call it the characteristics. And this is where the first nibble is all zeros instead of 0, 0, 1, 1. And then the lower nibble, or the lower 4 bits, this bit's going to be turned on, and we're going to have the letter D, the letter C, and the letter B. 3 bits that mean something. D refers to display on and off. And if it's 0, that means off. If it's 1, that means on. So you can actually turn the display on and off with this 1 bit. Normally you would want that to be on, so most of the time this is going to be a 1 in this position. The C refers to cursor on or cursor off. And once again, 0 is off and 1 is on. So normally, you're probably going to want a cursor, but maybe sometimes the cursor would be annoying. So you can make your decision one way or the other. Let's say we just want to have text on the display and we don't want to have any cursor flashing or anything like that, so maybe you would decide you want this to be a 0. No visible cursor. And then finally we have B, and this refers to blink. And once again, if you want the blink to be off, you set that to a 0. If you want the blink to be on, you set it to a 1. Let's assume here I don't want any blinking, so I'm going to set that to 0. Well, this corresponds to a 0, 8, 9, 10, 11, 12. That's a C in hex, so 0C is your hex code for configuring the display to be on with, let's see, what did I say? It was going to be the cursor is on, the display is off, and blinking is turned off. But this second part of the command in hex would change depending on how you set those various parameters up over here. And there's one more important one here. It's very similar. Remember, on this one, for these 3 bits to mean something, this bit here needs to be turned on. If we do the same thing with the upper 4 bits turned off, and this first bit in the second nibble being a 0, Now the meaning of these other 3 bits is different from what it would be here. In this case, this is going to be a 1, and the next 2 bits are the ones we're worried about, and that's going to be I, and that's going to be S. I means increment or decrement. So if this is a logical 0, that means increment. And if it's a 1, that means decrement. What that means is whenever you place a new character on the display, if it's set to increment, every time you place a new character on the display, the cursor is going to move 1 position to the right, and the next time you send something to it, the next character will appear at that cursor position, and the cursor will move 1 more position to the right. So essentially every time you send a new character to the display, they're always going to appear moving to the right, just like you would write them. However, the display controller can be set up to decrement the cursor, so when you add new characters they appear to the left. Normally you wouldn't do that, but sometimes you might. But for most applications you would want the cursor to increment, so you want to put a 0 in this position. And finally the S refers to shift, where 0 equals no shift and 1 equals shift. What's this mean? Well, I haven't actually tried it, but my understanding is that most of the time you're going to want characters to appear and the existing characters to stay where they are. Like if you're spelling out a word, the first character is going to appear here, the next character is going to be here, etc., etc., etc. as you add more characters. And that's because the cursor is incrementing. But what if you had a situation where you wanted the cursor to stay where it was, so the new characters always appear in the same position, and existing characters have to get shifted out of the way to make room for them? Like you keep adding characters and they keep appearing here on the screen, and all the other characters have to move to the right or move to the left. So that's the shifting function there. And if you set the bit to 0, then that shifting will not occur. The new characters will always appear at the position of the cursor, and the cursor keeps moving to the right. But if you turn the shift on, now the characters appear at the position of the cursor, but the cursor does not move. Instead, everything else shifts out of the way to make room for incoming characters. So again, you probably wouldn't use that too much, and we're going to assume that this is going to be 0 most of the time. So this works out to be a hexadecimal 0, 4. So that's another important code that you're probably going to want to use sometimes. I should say that most of these display controllers will default to the most common settings. So even if you fail to send it, this guy for example, or this guy, it'll probably default to these positions. It'll probably default to display on and cursor off and blink off, and it'll probably default to incrementing the cursor and shift being turned off. So you could take your chances and just not send these commands and it'll probably work fine. But if you're writing professional code where it's really important, it's probably good to put those in there to make sure the display works the way you think it should. Here are the only other 2 important commands that I want to discuss. We already know what happens when you send a command with the upper 4 bits all turned off and the first bit of the lower nibble being turned on. Then it's going to be expecting this. If the first bit of the lower nibble is off and the second bit is turned on, in other words in the 4 position instead of the 8 position, then it's going to be expecting the lowest bits here to mean this stuff. Now what if you send it where the 3rd bit is the only one turned on, or that's the 3rd bit in the second nibble, or if you're counting from this direction it's the 2nd bit or the one in the 2 position. This combination by itself means to reset. And what is it resetting? It's resetting the cursor. So let's say the cursor was last over here somewhere and you wanted to get it back to here. You would execute this command, this particular pattern, which in hexadecimal is 0, 2. So sending a hexadecimal 0, 2, regardless of what else is going on, will put the cursor back in the leftmost position. Now I'm not sure if you turn the cursor onto decrement and you send it to the home, will it move the home? Is this home then, or is this home? I haven't tried that, so if you want to do that, you might experiment with it and find out. I want to say this is always home, but I'm not absolutely positive. Finally, if you have all other bits off and you send the command with only the least significant bit, or the 1 bit, this refers to clear. This clears the display, so whatever junk you've got on there currently, if you send that command, it's going to wipe it all out, and it's going to look just like this. So it would make sense when you're first powering up the display that you do the initialization sequence, and even if you don't need to do these other things, you'd certainly want to do a clear. Now it seems to me that clear also includes reset built into it, because when I've done programs with these displays and I have some junk on there already and the cursor certainly isn't in the leftmost position and I've done only a clear, the next time I send data it appears in the leftmost position. So I think the reset is built into the clear, but once again I'm not absolutely positive of that. Anyway, the clear would be a hexadecimal 0, 1. So I'd say that these guys are very important, and these guys are very important, and probably this is kind of important too, because it establishes the mode of the display. These guys are probably more optional, but these handful of codes will get you a long way. And I should stipulate again, these are all commands. They're not considered data as far as the display is concerned. Of course, the computer that you have that's sending code to these displays thinks of everything as data, but as far as the display controller is concerned, these are all commands. And what does that mean? Going back to this pinout, it means that you have to make sure that the RS pin is logical 0 or grounded whenever you send information to the display. If you don't do that, it's going to think you're sending it data, and it's going to interpret that completely different. But if you have this as a 0, and since you're sending data to it, this has to be set to right, then it will interpret the binary stuff on those pins according to this chart. Now this second part's going to be a bit easier. If you've already sent your commands and got your LCD controller configured the way you want it to be, then all you have to do is send it data afterwards. In other words, the actual codes to specify what you want to display on the LCD screen. And everything in the data mode, and remember for data mode, this bit here, pin 4, must be set to a 1 or a logical high or 5 volts or whatever. And then again you're writing data, so this one's going to have to be set to 0 or grounded. Then when you send 8 bits to the display, it's going to be treated as data, and all data is in ASCII. So ASCII, of course, is one of the methods established for specifying alphanumeric text and punctuation on computers. And it's used by Windows, it's used by, pretty much every operating system. It's used by most devices, including these displays. So you have to get yourself an ASCII chart somewhere. These are readily available online just by searching for ASCII, and that's ASCII. So you get yourself an ASCII table. There's 256 possibilities in the ASCII table. There are punctuation, there's the numbers 0 through 9. There's uppercase A through Z and lowercase a through Z. And then there's various characters in other languages. The Hitachi controller, I believe, includes some Japanese characters. I don't think it's real big on characters from other languages like diacriticals and so on in, for example, German that might need umlauts and things. But again, you'd have to check the data sheet of the particular display you're working with. Some of the data sheets I look at seem to imply that the ASCII table is fixed. Other ones seem like they allow you to write an ASCII table to the display because they do have built-in RAM, and in many cases it's non-volatile, so you can set it up once and it'll remember that until you change it again. Other ones might need you to send the data every time you use it, every time you power it up, maybe as part of your initialization sequence. But again, check your data sheets for the particular display you're using. But I think it's safe to assume, as long as you're just using the usual A through Z, upper and lower case, numbers 0 through 9, and basic punctuation, you won't have to do any of that stuff or worry about it. It's just built in. You have to know whether you're thinking of sending the data as decimal or as hexadecimal, because the tables will show you both, and some will even show you the binary pattern. That's what it all boils down to. So once you've configured the display with the initialization and you've set it up so it knows how many lines and cursors and all that stuff, then you'll switch over and turn this bit to a logical 1 and start sending it the data for all the characters you want to display, and they will appear on the display in the manner that you selected by your commands that you sent earlier. And once again, except for the initialization routine, you can change the mode, I think, pretty much at any time by just sending it appropriate commands. You might start out with the cursor turned off, but then maybe later on you want to ask the person using this device a question, and then you want to put a cursor on there, and maybe you want to have the cursor flash so that it draws attention to the cursor, and the person who's using it knows that they have to maybe enter something on a keyboard, for example. So it's a prompt. At that point you may send it the command to turn the cursor on and make the cursor blink. And then later on you don't want that, so you send another command to turn those things off. So at that point you're sending it a combination of commands and data. It's all up to the application, and it's pretty straightforward. So that's my overview of how these work, and now I'm going to do a little demonstration. The thing I've got to test my LCD before I put it into my actual application, and this is all retroactive here, or retrospective I think is probably the better word. I've already got the application designed and working, so I'm kind of going back and looking at this as if I'd never done it before. And the device I chose to use, and I haven't done a YouTube video on this, but I'm probably going to. This is a product by an engineering professor in Thailand. He works at one of the universities, and he has, I don't know if it's a hobby of his or a side business, or maybe he does it really for the college and just sells some of them in addition to that, you know, for students to use or whatever. But it's intended to be an educational series. He has these little single board computers. They've got, it's not actually membrane, it looks like membrane, but underneath there are actual switches on the circuit board that have an overlay, and then you can click through a membrane onto pushing the actual switches. They all have an RS-232 serial port. They're all powered by a single wall wart power supply that's usually supposed to be 9 volts. They all include their own voltage power supplies. They include LEDs for testing and diagnostics. They include the same LED display. They all have a monitor program built in which drives this display, and then they've got the keyboard, and the monitor program allows you to do things like look at a specific address to see what data is in it, change the data at a given address. If there are registers in the microprocessor, there may be a key to select registers. In this particular one, there's a whole bunch of registers, so they're like shift functions on the normal keys over here. And the shift is obtained by pushing the register key. So this particular product here is for the 1802 microprocessor, but he has a whole series of these using just about every 8-bit microprocessor ever invented. So there's quite a few choices. They all look pretty much the same, but there are subtle differences in the circuitry and the keyboards and such. The serial interface here could be used in many ways. Probably the most common way to use it is to connect it up to your PC or something so that you can save and load programs, because none of these have any means to save your programs, and you'd have to retype them every time you turn it on. So being able to plug it into another computer and load in the program you want to run would be a nice time saver. They also all have expansion ports, so you can build your own expansion devices. Maybe, you know, run a little robot or something. Anything you can think up can be connected here. So I've got this device, and since I had it handy, I used it to experiment with my displays, and this is one of the ones I bought, like I said before. And these are so ubiquitous and so, you know, so common that this series of microprocessor trainers already has the header built in for interfacing with them. And even the monitor program in here knows how to use these, but it doesn't support actually using it. It displays a test message so you know it's working, but then it doesn't have any other commands to send data to the display. At that point, it's up to you to program this computer to send data to the display. And the display is not actually used by this computer. If it needs to display something to you, it uses these LEDs. So this is just a courtesy here, because I think the designer of these knows that a lot of people might want to develop a project that uses these LCD displays. So if I can get the thing to plug in, it'd be a good thing. There we go. Got the LCD plugged into the front. Now I'm going to discuss the typical program for operating these. This is a test program that I typed up for my own records. This was my first attempt that I actually got the display to work properly, and it has some stuff in it which isn't strictly necessary, but I thought I would go through it just to describe how a typical program might be built to control these displays. Because this is a machine language program written for the 1802, there are some 1802 specific things about it, but overall these are pretty common features that any microprocessor would have. So I'm going to be a little bit generic about this, but still describe a little bit of how the commands work. Whether you're using something in machine language, or whether you're using something like an Arduino or Raspberry Pi or something that programs in a higher level language, the same steps really need to be done. Now I want to step back from that. If you have something like a Raspberry Pi or an Arduino, there's going to be a whole library of little programs and subroutines that you can download from the web that are designed to control this type of display and save you some of the work. But I'm going to ignore those for the sake of this video and only talk about doing it from the ground up, as if you didn't have those routines handy and you had to write everything. So the first thing I'm doing here is I have to establish a time delay, and the reason for that is something I haven't mentioned so far, and that is that these displays, they basically have that little controller in there, and the controller is a little computer in and of itself, and it accepts commands and data and executes those with its own little built-in program to do things with the display. And just like with most other devices, they don't all respond at the same speed. So it might take a little longer to execute one command than it does to execute a different command. And sending data and displaying data might take a different amount of time than executing an actual command. So if you send data to it too quickly, or data and commands to it too quickly, it can get confused or it can miss some of the things you're sending. So you want to slow it down a little bit so you don't get ahead of the controller in the display. And the simplest way to do that is just to put little time delays in. You send it one thing and you wait a short amount of time, send it another thing and wait a little bit of time. Well, writing a lot of time delays in the program can take up a lot of code, so that's a very cumbersome way of doing it. So this particular 1802 trainer built in its monitor program has a built-in time delay subroutine which can be called by user programs, and it happens to reside at hexadecimal address F001. So the first thing I'm doing here is I'm establishing a register in the microprocessor that points to F001. You can see these two that are data. Now this is 1802 specific, the way it goes about doing it, but essentially the 1802 has 16 internal registers, each of which is 16 bits long or 2 bytes wide. Those are all for user, the user to decide how they want to use them. They're not predefined. However, one of them is always the program counter, and there's actually commands in the 1802 to decide which register is the program counter at any given moment. It defaults to register 0, and if you want it to be something else, you have to tell it to use a different register as the program counter. So we're starting out presuming that it's using R0. At some point it's going to have to jump to the routine at F001, so I need a place to store that, so I actually put it in this register, and I'm basically loading F0 and then storing it in the higher byte of register 3. Then I'm taking 01 and storing it in the low byte of register 3. So now register 3 contains the address of the subroutine, which is F001. And anytime I want to call that subroutine, all I have to do is tell the microprocessor to start using register 3 as its program counter instead of register 0 or whatever it is currently, and it'll immediately jump to that. And then there's mechanisms built in to the processor that you can change it back to R0, and it'll pick up where it left off, which is essentially a return from subroutine. So that's the 1802's peculiar way of doing subroutines, and this is the way you would set it up. It would be a little different than this on different processors and operating systems. Now the next thing to do is we have to know what is the address of the LCD display. On this particular 1802 trainer, it is memory mapped, so it's set up so it responds to 4 different addresses in memory. And remember that there's 4 possibilities for these display controllers. There's writing to data, there's reading from data, there's writing commands, and there's reading command status. And that uses 2 different control bits on the display. That was the RS or register select bit and the RW or read write bit, and between those you have 4 possibilities. So the way it's handled on this particular computer is that each of those possibilities is given its own address. So for example, if I wanted to send commands to the display, I would just write data to address 7200. And so sure enough, you see here I'm setting up register 4 to contain 7200 by the same mechanism I used here. I take it 1 byte at a time, I load it in, and then store it to the higher or lower byte of R4. So that's just setting up that, and it's setting up only 7200 hexadecimal, since mostly I'm going to be sending it commands. So then I have to configure the display. Once I've set this up, now I actually have to start talking to the display. So the first thing I do here now is I come to this point in the program and I load in a value of 38, and you may remember from before that 38 is the command for establishing how many logical lines the display is expecting to use and which font. So originally when I wrote this program, I expected to have to initialize the display. So I actually had a 30 in this position, and this was intending to send the 30 to the display 3 times to initialize it. And remember that 30 is the initialization code. So originally I had a 3-0 in this position. I loaded it in, and then I send it 3 times in a row. You can see how the code repeats 3 times here. I send it once, I send it twice, I send it a 3rd time to initialize the display controller. In between each one, I do this little thing here where I do a sep command, which is set P to 3. P is another internal register of the 1802, and it's basically saying which register is the program counter. And there are 16 registers, as I mentioned before, and they're numbered 0 through F. So this value 3 here can be any number from 0 to F. It's the D3 opcode, so D always means the set P, and 3 could, or the second digit could be 0 through F. At this time it's actually 3, so I'm saying set the P register to 3, and all that means is instantaneously the microprocessor is suddenly going to use register 3 as its program counter instead of the register it was using, and that means it immediately jumps to the subroutine addressed by R3, which is F001. And I know that F001 is the starting address of the time delay subroutine in this computer's monitor program. So by doing this, I'm essentially saying run the little time delay subroutine. When it's done with the time delay, it'll jump back. It'll reestablish R0 in this case as the program counter, and it'll pick up right where it left off. Now I'm going to store my value on the D register, which again it was 30. It's going to do it a second time, call the time delay again, call it a third time, call the time delay again. Well, I found out that simply turning this microprocessor kit on sent the initialization code to the LCD if it was plugged in, and therefore it was not appropriate to send it again. Instead of rewriting the code to take those out, I just replaced the 3.0 with a 3.8, which we remember is no longer the initialization code. Now it's the code that, or the command that establishes the number of lines and the font. And it doesn't hurt to send that as many times as you want. It doesn't make any difference. So by changing 3.0 to 3.8 here, I've essentially taken this block of program that's supposed to be doing an initialization, and instead I'm just sending it the 3.8 command 3 times, which is pointless, but it doesn't hurt anything. And I didn't have to rewrite my program. Next up, I load in a value of 0.1, which we remember is the code for clearing the display. And once again, I store it out to address 7200, and then I do the time delay again. So the display will be cleared now. And now I load in a 0.2, which we remember is the reset, which isn't probably necessary, but I sent it anyway because it was part of my experimentation. So I load 0.2 in, I send it out to 7200, which is again the command, the address of the command register of the display, and then I do my time delay again. Finally, I get down to sending it some actual stuff. The data register on this computer, or on this display, when it's plugged into this particular computer, is addressed at 7201, whereas the commands were 7200. The data is 7201, as long as I'm writing to it. Again, this would be different depending how you interface the display with your particular controller. But by incrementing register 4, I've essentially turned 7200 to 7201 in the shortest possible way of doing it. Now I load in a value of 50, and I send it out to register 4 now, or to the address that's in register 4, which is 7201. So I've sent it the value of 50, and because I'm sending it data now, that means this 50 is not a command, it's a ASCII character in hexadecimal. And then I do the time delay, then I load in a 6.1 hexadecimal, send it out, do the time delay, load in a 7.5 hexadecimal, send it out, do the time delay, and finally load in a 6C hexadecimal, send it out, and there's no need to do a time delay after that. I'm just going to halt the program by sending it a 00. That's the way it's done on the 1802. Different processors can do this in maybe different ways. Some processors don't have a halt command, and you'd have to do something else here. Either make it do an infinite loop just to kill time, or send it back to a monitor program or whatever. But this sequence of commands is the first way I got my display to work in a way that was predictable and I could do what I wanted with it. But it's a little clunky. I didn't like sending it all those time delays, and the downside is I don't know how long the time delays really need to be. They are published, but they're all different, and it's very cumbersome, and you don't want the display access speed to be unnecessarily slow. But if you're just going to have one time delay value, like I have one subroutine here to do time delays for me, I have to set the time delay to always be a long value, the worst case scenario. So that means that this code is executing more slowly than it needs to run. So I'm going to now review a revised version of the program which does it a little slicker. So this is my second version of my LCD test program for this particular computer. And it starts out by establishing a jump command, or it's called a branch command on this processor. And it's a short branch, so it's only going to jump within the 256 byte section of memory that we're currently in. So I only have to specify the lower 8 bits, which is a 0A hexadecimal. The program is actually starting at 8000 hexadecimal, or 8000 hexadecimal, which means I'm actually telling the processor to jump to address A00A, and that's down here. So the first thing I'm going to do is I'm going to load in a value of 72, and I'm going to store it in the high byte of register 4. I'm going to get a 00, store it in the low byte of register 4. That means register 4 contains the address 7200. And we may remember from before that that's the address on this computer that I have to use if I want to send a command to the LCD display. Then I do the same thing here. I load in a 72 stored in the high byte of register 5, load in the 02 and stored in the low byte of register 5. So now register 5 contains the address 7202, which I happen to know is the address for reading the command status from the LCD controller. Then down here I set up register 6 in the same way with F8 01. Let's see. Yeah. I've lost my place here. Okay, yeah, so 72 goes into the high byte and 01 goes into the low byte. So I've set up R6 to have 7201 in it, which is the address used for sending data to the LCD display. Now I'm not going to try to read data from the LCD, so I'm not setting up address 7203 in a register. I won't need it. But I do need to do one more thing where I'm setting up a register, and here I'm going to set up register 3 first with an 80 in the high byte and a 03 in the low byte. And that's going to be used later because I have a subroutine starting at A003. So remember from before that I can call subroutines on the 1802 by simply putting the address of the subroutine in a different register and then suddenly changing the register pointer to point to the new register, and that makes the processor essentially jump to the subroutine. So by doing this, I'm pretty sure that I'm setting up the address of this subroutine in register 3. So let's go on now. Once I've established all of those, I'm going to do a SEP3, and we remember from before that means I'm setting the P register with the number of the register that's now going to become the program counter. So I'm setting it to 3, and I know that I just set R3 to contain the address 8003. So by doing this D3 opcode or SEP3 command, I've essentially jumped to the subroutine that's located here. So let's see what that does. First thing it does is it loads into the D register, which is what the accumulator is on the 1802, the data from the memory location that's pointed to by R5, which I happen to know is 7202 because we just set it up a little earlier. So essentially this is doing a read command from 7202, which is the command status of the LCD controller. So I'm essentially reading in here the status bits of the LCD controller into microprocessor memory. And I happen to know, it's not shown here, but I happen to know that the most significant bit, essentially this, here's the data I've just read in. It's an 8-bit of data, and the only thing I'm interested in is this most significant bit of the byte I've just read in. I want to know if this is a 0 or a 1, because this is the ready bit. As soon as the display controller is done with whatever it was busy doing and it's ready for a new command or new data, it's going to change the status of this bit to indicate that it is now ready. So on the 1802 microprocessor, the way I test for that is by logically ANDing a mask against this. So that's what it does here. I do a logical AND with the data that follows, and the result goes back into the D register or the accumulator. So essentially this is the value in the D register, and now I'm going to take a mask, which is 80 hexadecimal, which means it's this pattern. Again, this is the mask, and what they're doing is the processor is going to logically AND these two together and put the result back into the D register. So let's say that this ready bit is set to 0. If you AND these two bits together, we get a 0, same thing. And a 0 and a 1 ANDed together is still a 0, so the whole D register is going to be all zeros, which is a value of 0. But what if the ready bit was turned on? Now these are all going to solve the same when it ANDs them together, but here a 1 and a 1 ANDed together is a 1. So now I'm going to have a value of 80 in the D register after doing that command, which is decidedly not equal to 0. So what we've done here is we've tested for that one bit by AND masking it with this 80 hex value. Now the next thing that the subroutine does is it does a branch if not 0. So essentially what it's doing is it's going to look at the value of the D register and say, is it 0 or not? And it's branching if not 0, so if it's set to any value besides 0, such as this, it's going to branch. And it's a short branch, so it just looks at the next byte, which is 03, and it sets the program counter lower byte to 03. Since we're already working in the 80 part of memory, and we changed the lower byte to 03, we're essentially jumping to 8003, which is the beginning of the subroutine. So we said, hey, D was not equal to 0, so let's jump back and test it again. We're going to retrieve the status from the display again. We're going to AND mask it with 80. We're going to check once again to see if the result was 0 or not. Only when this ready bit turns off, turns back to a 0, does the D register finally become 0, and that is the indication that the display is ready. So now the branch, if not 0, sees that it really is 0 now, so it continues on instead of branching. And the next thing it goes is it finds another branch command. This is unconditional. It doesn't have to test for anything. It's just going to replace the lower byte of the program counter with 02. So now it's going to go to 8002, which is this little one-line subroutine, and it has a single command in it, which is to change. It's a SEP 0, so it's changing the program counter back to register 0 from register 3. And since we started out with it being in register 0, which is what it always defaults to, we essentially jump back to wherever we were before we do the subroutine, which is back to here. Here's where we did the SEP3 command. So now we've essentially waited for the ready bit to be cleared, saying that the display is ready for more stuff, and then the subroutine kicks us back to this line. So instead of doing the way we did it in the first program, where after every command or piece of data I have to jump to a subroutine to do a time delay, here after every command or data byte is sent out, I have to jump to a subroutine to not do a time delay, but instead look at the ready bit of the LCD controller and wait till it says it's ready, and only then send it the next thing. So I'm not going to repeat describing the jump to subroutine every time. I'm just going to go down the list. So we've checked to see if the display is ready. Now we go and get an immediate value of 01 and store it out to the display at register 7200 hex, which is the command register. So I'm sending it a command still. So what is a 01 when it's treated as a command? Well, I remember from before that a 01 is the command to clear the display. So what I'm really doing here is I'm saying send the command to clear the display. Once again, I call the subroutine to do a time, or not do a time delay, but wait till it's ready. Then I retrieve a value of 50 and I store it to the address pointed to by the 6 register, R6, which I know from before I set up as 7201, which is the address used for sending data to the display. So essentially I'm storing the value of 50 to the display's data register. I do the time delay again, or not the time delay, but I wait for ready. Now I retrieve a value of 61 and store it out to the display's data register. I call the subroutine for checking the ready again. Then I retrieve a 75 and do the same thing, send it out. And then finally I retrieve a 6C and send it out. And after the subroutine is done, then I essentially put a halt on here. Or I don't do the subroutine the last time actually, I just send the value out to the display and then I do my halt. So ultimately I've done the same kind of stuff. I've done some basic configuration on the display. I've cleared the screen. In this case I didn't send a command to reset the cursor. I presumed it was built into the clear command, and I think that's right. So I didn't put a program step in here for that. The major difference between the two programs is that this is a later program, so I didn't send it all the Flooby dust that I started out with the first time, where I was unsure about initializing it. And I replaced the time delay being called after every command or data with a routine that checks the ready, and therefore we can shovel information off the display as fast as it can possibly take it. So that would be more efficient. Either way really works, and at the speed processors run, really the time delay method works just fine. Either one works. Anyway, so the next thing I'm going to do here is actually program this in just as a demonstrated proof of concept. So I've just powered my 1802 educational computer here up to power, and it's booted up. And the display doesn't really flash like that. That's just the camera's frame rate in video mode. It makes it look like it's flickering. In reality, it's a very stable display. But you can see that the firmware in the monitor program here has configured the display already and has sent some data to it to display CDP1802, and there's 32K of RAM. It does nothing else with it after this. It has no use for the display. It's just sending it this data to essentially test that the display is working. Anything else that I'm going to send to this must be sent by me and my user program. So I'm going to ignore this for the moment and just use this display, but I'm not going to bore you with the mechanics of entering this whole program, other than going maybe the first few steps just for jollies. I happen to know that user memory starts at 8000 hex, and for my own purposes, when I'm talking hex, I usually say it as if it's decimal, so I'm going to say 8000 hex, although of course it isn't really 8000. It's a completely different value, but it's just a shorthand way of saying the address instead of saying 8000. So there's a key on here to immediately set the program counter to 8000 or 8000, so I don't have to enter that value. And it's saying by the dots here, it's prompting me to enter data. I know my first data is 30, so I push 30, and now I've got 30 in 8000 hex. I want an output 0A in the next one, so I push the plus button to increment the address and put in my 0A, and so on. I'm going to do the whole thing now without the video rolling. So I've entered the whole program in here, and now I'm going to set my program counter to 8000 hex again, and I'm going to tell it to go, which tells it to start running the program there, and it's going to happen in a blink of an eye. It's going to set up all my registers, then it's going to send the command to clear the display, and it's going to start sending it data, and we should see my name appear in a blink of an eye. There we go. And now the display stopped working because I sent the halt command as my last command, and that causes everything to stop. The processor is no longer running, and the display is just holding whatever I sent it until I tell it to do something else. I can reset the processor, get it running again. When it does that, it's going to send the initialization code again and rewrite what it wants to have on the display. If I go back to program counter and go again, it'll send the whole string of commands and data, and once again I've got my name on it. So I hope this demonstrates the basics of how to use this kind of display in your own project, and I hope you found it useful. So just to tag on to the end here, the method I described to experiment with these LCD displays is using a complete microprocessor trainer that can be programmed and used to output commands and data to the display, but you can actually experiment with them using a much simpler approach that isn't really that much work really when it gets down to it, and it actually works slowly enough you can see what's happening, so there's an advantage. So I'm going to go over that real quickly here. All you need is just a few resistors, a potentiometer, capacitor, some switches, and that's about it. Oh, and a 5-volt power supply. So remember, I had my diagram here which showed the purpose of all the pins on the display, and here's a sort of minimal test rig. If you have a 5-volt power supply set up, and the typical LCD module these days, not counting the backlight, is set up for 5-volt power and typically a very small amount of current, maybe 1 milliamp or 2 milliamps, so it doesn't take very much. Really, any supply that can give you 5 volts regulated should be able to supply the requirements of these displays. Now if you want to run the backlight, it's a little more robust, and I'll talk about that shortly. But you'll need a potentiometer. 10K is the recommended value, and you can see here it's connected between the plus and the minus of the 5-volt supply, and then the wiper is connected to pin 3. The plus of the power supply is connected to pin 1, and the minus of the power supply is connected to pin 2. And I'm also showing the symbol for V plus and ground here, so whenever I use it elsewhere in this schematic diagram, you'll know that it means the plus side or the minus side of the 5-volt power supply. Coming down to the backlight, it turns out this particular LCD, and again they're not all exactly the same, so check your data sheets. This particular one does have a built-in resistor or current regulator for the backlight. It's just built right in there. And so it does not need an external resistor to limit current to the backlight LED. Still, I would recommend putting in a small value resistor. I suggest maybe 10 ohms. And then if you want to try different displays and you find that there is one that does need a resistor, you'll already have a place for it on your test rig, and you can put in a larger value if required. And even if the display has its own circuit for handling current limiting, that 10 ohms isn't going to hurt anything. It's a low enough value, so that'd be my recommendation. Anyway, so now as for the commands, the RS command, or not command, but the RS signal, the RW signal, and the clock enable signal. The typical way to handle these, at least the RS and the RW, and then the 8 data bits, D0 through D7, is through this one typical circuit that I've drawn out one time. Get yourself a bunch of 4.7K. The value's not that critical. You could use 10K here. I probably wouldn't use much more than 10K, but that would certainly be a good value. I wouldn't go down as low as 1K, because everything you do here is just going to take more current if you go lower and lower on resistance. And that'll increase the power supply requirements here, but it won't affect the display at all. 4.7 is probably a good round value, and it's a common value. So connect all these pins, every last one of them, through its own resistor to V+. And then, for everything except the clock enable, get a little toggle switch, some sort of maintained switch. And you could use, if you have a bunch of little toggle switches, you could use these. If you have perhaps some dip switches like this would be a very economical way of doing it, although a little bit tedious to set because they're so small and you pretty much have to do it with a small screwdriver or the end of a pencil or something. There's another small dip switch. But these would certainly work. And actually, if you can get your hands on some of these puppies, this is a little rotary switch that is brought out essentially to do the same thing as a bunch of toggle switches. You have to make sure you get one that isn't already encoded. This particular one is. I think it's set up for BCD perhaps, but you can see there's a little knob on there, and if you turn that you can see which position you're going to. This one's already set to 0, or maybe it's a D. This one might actually be hexadecimal. I'm going to try it out real quick here. Yeah, D, C, B, A. So this one is set up for hexadecimal. So you could actually get a couple of these and connect them up for the data so that the upper 4 bits are hooked up with one of these, and then the lower 4 bits are hooked up with another, and then you can actually just set the two knobs to the 2 digits of the hexadecimal code you want to send out, whether it's a command or data. That would be a really handy way of doing it, again, if you can lay your hands on these. Or there's other versions of these too, but you want to be able to set any possible combination of zeros and ones on these 8 lines, either in 2 groups of 4 or collectively. So anything that you might have in your junk box or lay your hands on quickly would work for that. Here's a slight elaboration on what I was talking about here. If you can get your hands on some hexadecimal coded rotary switches, you'd need 2 of them, one for the upper 4 bits and one for the lower 4 bits. You can connect them up like this, so they would be hexadecimal coded, which means they're going to have a common pin that you could connect to V plus or the 5 volt, positive 5 volts. And then they're going to have outputs that are binary weighted, 1, 2, 4, and 8. And you'll connect those to the corresponding data lines of the display, such that the first one of these switches would connect to data bits 0, 1, 2, 3, and the second one would connect to 4, 5, 6, and 7. And then all you'd have to do is set the two switches, and when you have it selected to one of its 16 positions, internally it will connect this pin to the appropriate combination of these pins to bring them to the appropriate binary pattern that corresponds with whatever you've set here. And because the switch is pulling the signals high, you need something to pull them low when the switch is not active. And for that, you're going to want to use some pull down resistors. So for example, like this. It's amazing how bad my penmanship gets when I'm trying to write fast. Anyway, this would be the approach here. So the resistors are pulling these to logic 0. The switch pulls them to logic 1 when the appropriate pattern is selected. And then a small momentary push button connected to ground for the clock enable line. And to debounce it just a little bit, it's probably good to put a small value capacitor. I would suggest, 0.1 microfarads or something, but it's probably not that critical. Even a real small electrolytic capacitor would work. Whatever you've got in your junk box really would probably work. As soon as you push the button down, it's going to pull this line low against the pull-up resistor. And that's what all these resistors are, is they're pull-up resistors. So normally they're trying to pull these lines up to 5 volts. But when the switch is closed, the switch will pull it down to 0 volts. And when the switch is reopened, the resistor will pull it back up. In the case of the button, it works just like the switch. When you push it, it drags this down to 0 volts. And then when you release it with your finger, then the resistor pulls it back up. But the capacitor there slows it down a little bit so that there is less ringing on the signal. These other guys are not so critical because any ringing that's going to happen on here is going to happen so quickly that it'll be over before you get around to pushing this button. What you don't want to do is having any ringing going on the RS, RW, or data bits at the time you push the button, because then it might clock in the wrong value. You want these lines to all be stable at either 0 or 1 before this is pushed. So just the fact that you're going to have to move the switches and then move your hand over and push the button is going to be plenty long enough for any of these other guys to stop ringing. But you probably do want to slow this down a little bit. In reality, you could leave the capacitor off. It'll probably work just fine. But anyway, so there, if you've got just a handful of switches, some resistors, maybe the capacitor, potentiometer, and a 5-volt supply, you'd have all you need to send in commands and data to drive these displays. And once again, you could see every step of the way what's happening on the display as you're doing that. It's going to be slow and tedious, but it'd be very educational, and you can definitely see what's happening. One other thing I want to cover here is that I looked up the data for this particular display, and this is the one, remember, with the long composite LED backlight assembly built into it. And it's rated for 100 milliamps nominal, so it could be more or less than that, but 100 milliamps is the nominal value that's going to be required to power it. So your 5-volt supply is also going to power this, so you have to make it good for at least whatever the backlight on your display is going to require. And most power supplies that are regulated are going to be good for many hundreds of milliamps, so they should really all be good enough to power this, backlight included. And just to tack on another comment, remember that even though I did not have to do it in my 2 demonstration programs that I wrote from my microcomputer, when you're running the display all by its lonesome this way, using this type of test rig, you do need to send it that initialization display before you start sending it commands or data. So don't forget to do that.